Well, thanks very much for the introduction and the chance to talk. This, I hope, is a talk that will demonstrate what I think is really the potential for machine learning to augment our data assimilation systems and solve some pretty difficult problems that we have to face in Earth system data assimilation. And the specific problem is focused in this talk on the sea ice assimilation, well, sea ice assimilation in the current atmospheric IFS. And on the right, we have the assimilation of microwave radiances sensitive to the surface from various instruments in the all-sky radiance assimilation path in the 40 var for atmospheric data assimilation. And this is not yet done over sea ice areas. And the reason is that the sea ice field is very important to the microwave radiances, and that's held fixed, and it comes on a long chain from the ECMWF Ocean 5 analyses, which themselves ingest the ISDA level 4 daily sea ice analysis, which itself is based using data assimilation on a level 2 sea ice fraction retrieval, which itself is just a heuristic retrieval from the microwave radiances, the same microwave radiances that we're assimilating. And the problem there is that's a suboptimal use of observations, and particularly the long processing chain gives a 48-hour delay in getting the sea ice information to the atmospheric analysis. And because it's so out of date, and because there are imperfections in the analysis, it's not a good fixed constrained boundary condition to have for assimilating the microwave data over sea ice. Now, in an ideal world, we would do coupled data assimilation, get rid of that additional path, and we would assimilate the radiances directly over all surfaces in all sky conditions into the atmospheric data assimilation system and infer the sea ice there, and use coupled data assimilation, which isn't the subject of this talk, to share the information on sea ice with the ocean and sea ice analysis. And so, yeah, the focus of this talk is really the radiance operator for sea ice. And what we need there is a forward operator for microwave radiative transfer over sea ice and snow surfaces. And that's simplified slightly in this work to representing the sea ice surface emissivity. But that sea ice surface emissivity is a very difficult problem because it's so variable in time and space, and it depends very strongly on the snow and the ice microphysical properties, and many other aspects of the snow, the sea ice and the snowpack, like the age of the sea ice or the wetness of the snow and so on. Now, we don't actually have those things available, which is why there's no physical data assimilation of the microwave radiances over sea ice at the moment. And so the focus of this talk is trying to find alternative empirical approaches to solve that problem. And it's a chicken and egg problem because the physical operators are not good enough globally yet. So we want to train an empirical observation operator. Well, if we want to do that in the normal way, we would have to have inputs of all of the various sea ice and snow properties, the microstructure, snow and ice variables, the density, and so on that drive the radiative transfer, and those are not available. And in order to get an analysis of all those relevant snow and ice surface variables, we would probably need a physical observation operator to infer them. So we need both of those things simultaneously. Long term, the problem will be solved physically. Physical observation operators for snow and sea ice are coming on very fast. There's a very nice piece of work there. And we're also going to need more sophisticated physical modeling of the sea and the sea ice and the snow to represent things like the microstructure that's needed for radiative transfer simulations. But in the meantime, and as a stepping stone and a bridge towards the physical approach, is the idea of training an empirical observation operator simultaneously with an empirical surface state. Now, before we get to that, I just want to talk about the physical side of this, that the core equation that's being used here is the surface emissivity, which strongly affects the radiative transfer and the brightness temperatures at the top of the atmosphere. And that whole surface emissivity, E, is a function of the fractional concentration of the sea ice and of the ocean, expressed in the sea ice fraction here, the C parameter, and then the emissivity of the ocean, which is well known, and the surface emissivity of the sea ice, which is poorly known. And in terms of frequency and polarization, so the numbers of the frequency in gigahertz, V and H are the polarizations, vertical and horizontal. This is the spectrum of microwave ocean surface emissivity. It's got a sawtooth pattern, which indicates strong polarization, and it increases with frequency. Whereas the dashed line with a question mark is a guess at what the sea ice emissivity spectrum might look like, but it's so variable in space and time and so poorly known that we don't have models for it. Now, these physics, if we can get them represented right, will give us very good, clear ways of estimating the sea ice fraction due to the contrasts in the surface emissivity, the contrasts in the polarization, and the contrasts in the frequency dependence. of the two different surface emissivities. Now, if this was a physical problem, we could represent it using a network, and this is a Bayesian network representation of the problem. At the top, we have Y, which are the observations being simulated by the network. They're being compared using a cost function to the true AMSA2 observations. These equations here represent the atmospheric radiative transfer, the clouds, precipitation, and water vapor. The whole surface emissivity that we saw on the previous slide, E, the equation is represented here. And the sea ice fraction is input to that equation at the observation locations, and it's interpolated using an interpolation operator H from a map of the sea ice. And the code here is that if you've got a solid block outline is a fixed parameter, dependent parameters are thin outlines, and the dotted line outlines are parameters to be estimated. So this is basically just a data assimilation problem for estimating the sea ice fraction. But the problem is you can only do that if the surface emissivity of sea ice is well known enough. And of course, we don't know that. So we need to add a whole new dimension to the problem. And we're adding this aspect at the bottom, which I'll highlight through adding words onto the plot. So there's an empirical sea ice emissivity model, F-empirical, and that's a neural network that models the spectral and polarization dependence of the sea ice surface emissivity as a function of known physical inputs, ZB, and unknown weights, the dashed circle around the W, which are the trainable weights of a neural network. And in the same way as there is an observation operator for the sea ice fraction, there are empirical properties, X ice, which are on maps, are interpolated into observation space, that's the lowercase x, and they're also input to the empirical model. And so those empirical parameters are completely empirical. We won't know what the meaning of them is in advance. The only thing that we choose is the number of them, and I've chosen 3 based on sensitivity studies. And the point is this model will generate itself and its inputs at the same time. And this is all solved and implemented using TensorFlow and Keras, so not in a standard data assimilation system, but still solved variationally. Now, just to highlight that part, the most complicated part of that, the empirical part, we might call this an empirical state method, because there's an empirical state representing unknown geophysical properties of the surface, like the microstructure of the snow and the sea ice, which are interpolated to observation space to give the empirical parameters at observation location, and then a neural network model, an empirical model, based on some trainable weights, then creates the sea ice surface emissivity. So the training process simultaneously learns the empirical state, the meaning of the empirical state, and a model to go from the empirical variables to the physical quantity. Now, just an aside on how this fits into machine learning, this is really an unsupervised learning generative ML approach. We're in the chicken and egg situation, means we don't have the training data to train a standard model based, a standard neural network based on the inputs and the outputs. We're really trying to train something called a latent space, and in the idea of the decoder neural network, which goes from a statistical representation, a small compact statistical representation of a phenomenon, back up to a reconstruction of it. The example from machine learning that does that, that's most widely known, is the generative adversarial network. And this example here is snowflake images. Very nice example. Snowflake images from taken from an aircraft camera on the top line and reconstructed using this decoder network approach based on variables in the latent space. So there's a statistical description of the snowflake image that's mapped back through the decoder into an actual picture of the snowflake image. And because it's statistical, you could generate a random vector in the latent space and also generate random but completely realistic looking snowflake images, which is the bottom row here. Now the GAN is too complicated for what we're doing here, but it's a nice inspiration. And so this empirical state method is basically part data assimilation and part a kind of generative machine learning. So just to put some numbers on things, this is a more simplified diagram of the network that's being estimated. And the training is done simultaneously on 1 year of AMSA2 radiance observations on 10 channels and different polarizations. And the things highlighted in colors are the things that are being trained. Now, there's a very compact sea ice surface emissivity model, and that's reduced just down to 80 trainable model parameters. And the idea is that represents sea ice surface emissivity across the globe and at all locations in a very compact model. But what's not compact is the surface state, and we're estimating the sea ice fraction, a physical variable, and 3 empirical variables representing the surface properties that drive the sea ice surface emissivity. And that's done on 365-day grids with 40-kilometer resolution. There are various loss terms, which I won't have time to talk about, which regularize the problem and make it more like data assimilation than machine learning. And that's trained in TensorFlow and Keras. So the results very quickly. We have the initial simulation of brightness temperatures in the left-hand panel at 10 gigahertz V polarized and 37 gigahertz V polarized. And that's based on initial conditions, which are a monthly mean sea ice fraction and a completely flat estimate of the sea ice surface emissivity. Now, when the network trains, that's the middle column, we get brightness temperatures that are much closer to the AMSA2 observations, which are the right-hand column. And in terms of departure, just shown on the bottom row for the 37 gigahertz brightness temperatures, we have very big departures up to 30 Kelvin based on the initial conditions, the initial model, and the train network fits the observations almost perfectly. Now, the empirical model, it actually starts to represent physical things, but in a statistical, empirical kind of way. So this is a map of the Arctic on the 7th of November during the rapid formation of the new sea ice. But part of the sea ice is old, and this multi-year ice comes up showing on these maps of the empirical properties that drive the surface emissivity empirical model as positive values of property 1 in particular. And the emissivity spectra is shown on the bottom left. That shows the sea ice as being relatively flat in terms of polarization, but dropping off with frequency. And then there's clearly another domain where empirical property 1 is blue, so it's strongly negative, and other properties have different settings as well. And this is new ice that's formed over the last month, and in this particular example, just in the last few days. And this new sea ice is much more strongly polarized and has a very flat surface emissivity spectrum. And so although it's an empirical model, it seems to be capturing real physical details of the problem. Just to show the sea ice fraction retrieval itself on the same day, here on the top left is the monthly mean initial conditions before training, the retrieved sea ice surface emissivity on that day from the empirical hybrid physical model. And below is the existing initial guess and fixed guess of sea ice that comes from the Ocean 5 processing that's available to the atmospheric data assimilation. And the bottom left is the difference between the two. And you can see that over tens of thousands of kilometers of the Arctic Ocean, particularly because the IFS estimate is delayed by 48 hours, the reality and the original IFS estimate are very different indeed. Now, that's really where this talk, that's as far as this talk can go in terms of covering this work, but it carries on. I'll show you a few more slides on how far it's got. So that was the offline training I was just describing, but that surface emissivity model can then be put into the IFS for atmospheric data assimilation as a fixed model, so it doesn't get further trained. And it needs these empirical inputs, but they can be estimated as part of 4D VAR using a sync variable approach. And the benefits of this are to retrieve a high-quality sea ice fraction directly from the radiances within the atmospheric 4D VAR system, as I showed in the second slide. And also to be able to use surface sensitivity microwave observations in the proximity of sea ice is giving some good good forecast benefits. And this example here shows the blue areas around.
Alan, you have 2 minutes left.
Great, thank you. So around the sea ice, we're reducing this. That's what the blue colors indicate. We're reducing the temperature error in 850 hectopascal temperature over the first few days. And this has progressed far enough that it's part of the candidate 49R1 cycle of the IFS, hopefully to be implemented next year. And just some pictures to show you how this is working. This is the former IFS sea ice concentration coming from Ocean 5. The main thing to notice here is what's missing. This is the island of South Georgia, and I'll show you what's missing in a moment in the real AMSA2 observations. So this is the sea ice of the Antarctic moving slowly with the currents. And these are the new retrievals, much more noisy in the area of the pack ice in the Antarctic, but this feature is moving rapidly towards South Georgia over a period of a few days. And that feature is real. We can see it in high resolution images. This is Olchi channel 10, 1 kilometer type of resolution imagery. And that big white thing is a large iceberg. You can also see underneath the cloud. It's a bit hard to see, but the much more speckly picture of the sea ice fraction from the AMSA2 retrievals is actually real. There is some very strong heterogeneity in the sea ice at this time of year. And so zooming in, there's the 40 kilometer resolution AMSA2 retrieval of this iceberg. It's the A68 iceberg. And there's the Olchi retrieval on the same grid. And there clearly is a very good spatial analysis of the sea ice fraction. So just to go to the final slide, just to summarize the fundamentals of this approach, which I'm really excited about. I think it could be applied to many other problems that are similar in Earth system data assimilation. And then the main three things are, first of all, that we don't just have to use our existing data assimilation frameworks. We can use machine learning tools like Keras and TensorFlow, which can also provide a flexible way of solving problems through variational minimization. They're just not for neural network training. And the idea of hybrid physical empirical networks with physical parts representing our existing knowledge of the physics and empirical parts, and in particular solving the chicken and egg problem by simultaneously training both the empirical version of the geophysical state that we don't know and an empirical model to go from that empirical state to the observations. So thank you for listening, and I'll take questions if there's time.
Yes, thank you, Alan, for this nice talk. It's indeed a topic that many of us struggle with, the chicken and egg problem. Let's see, there is no questions yet. So I suggest, Alan, that you stay in touch with the YoPad and see if any questions pop up in the next minutes. And then if you would be so kind to answer them on the YoPad, that would be great.
Sure.